Hi guys, hope all of us are doing great. Today we're going to look at one of the characteristics of integrals, and in this case I want us to be keen of course on the closed intervals that we're going to give for this specific illustration. So I'm going to have an example of this specific coordinate system whereby I'm going to have the y and x, but I've intentionally extended the x-axis so that we can be able to have of course an illustration from that. So suppose we have a function that is continuous and integrable over closed intervals, and I'm going to give this one as an extension of a along the x-axis, positive x-axis, and an equivalent extension of a negative a on that specific x-axis. So if this one is a function of y is equivalent to fx given as such, we can be able to give a definite integral representation for this specific function, whereby we're going to have the integral between this is going to be negative a and a of a function f of x dx given as such. So if we were to be able to allocate this a numerical value, if it's 1, then this is going to be equivalent to 1. If it's 2, then this is going to be equivalent to 2. So the extent of the stretch of a from the 0 or the origin is going to be a value a, and also, or rather the magnitude also is going to be a given as such. So the stretch for between these two closed intervals can be given as 2a, and in this particular case then therefore, if you were to represent the definite integral for this specific function and be perhaps try to find the area under the curve, we're going to see that we can be able to give these specific areas for a and a prime given as such, whereby we're going to have a equivalent to we have this one as a prime. So the area a equivalent to a prime respectively. So for us, in order to evaluate this entire area bounded by the curve and the x-axis, we can be able to say that this is basically the whole area is equivalent to a given as such. So from this specific analogy, given a value for the function of the integral between the lower limit of negative a and a, we can be able to write this specific integral as we said, of course, over the integral of constant multiples. We're going to have this value for 2 taken out, and then we're going to have it from 0 to a, whereby this one is going to, of course, imply that we have taken the area of one portion and multiplied it by 2, which is going to form our constant multiple given outside that integral sign as that, and then we find the area of one particular region, perhaps for a or a prime given as such. So this basically is going to represent the same interpretation for this specific interval, and this is going to be applicable especially if we have what we refer to as an even function. Now suppose we have an odd function, whereby of course we're going to see that if this particular function is going to be odd, then therefore the value for these integrals are going to be equivalent to 0, and we're going to have that one perhaps using different illustrations. Now suppose we have an integral that is having a value different from this specific unit of a, or perhaps if a negative is not equivalent to that value for or rather a is not equivalent, or rather this the value for the negative along the x-axis, the magnitude is not the same as the first one. I can be able to just give it a graphical representation given as such. So suppose we have a function that is continuous and integrable over these closed intervals for a, b, and c. We can give this one as a function of f of x over those closed intervals given as such. So we're going to have this one generally given as a representation of an integral, whereby we're going to have the integral from a to c given of a function f of x dx given as the integral between a and b, which is basically going to be this region of the function f of x dx plus the integral between this is b and c of the function fx plus dx fx dx given as such. So this one implies that we're going to combine, we are trying to find the area under the curve we're going to combine a1 and a2, which basically is going to be the integral for AB, which is a region for A1, and BC, which is a region for A2 given as such. This is going to give us a general representation for the integral between the closed intervals A and C using that general formula. So we can give various examples for this, and suppose we had this specific function defined, we can be able to have a specific value or numerical values for this, and we do a substitution, and therefore this is going to give us a general impression of a function which has got continuous variables or continuous for these closed intervals given as such. So I hope that this is going to be more elaborate in our discussion, but that is basic for us to remember is that in case we have a function that is over closed intervals, this one, another value of an interval in between can be given as a summation of these individual intervals, and that is going to give us a general representation for that specific interval. So I'm not going to give an example for that, since I hope that this is going to be more elaborate for if it's applied on another specific values that we may assign for this, perhaps 2, 3, and 5. Then we're going to just do specific substitution for this given a function, perhaps of a particular value, in this case perhaps 3 squared plus 2 given as such. So in any case we come across it, then we're going to do it appropriately. So I hope that is comprehensive. Let's catch up in our next video. So that is it for now, guys. Bye. God bless.